Okay, good morning. Uh, Today we're going to continue talking about different enumeration systems. We're also going to talk a little bit about extended Euclidean algorithm and some other cool things. So the first thing we're going to talk about is going to be the three bases, the three new bases I started discussing last time. But before we move on, do you have any questions? Okay, so I have a question to go over something similar to 3.28. And let me here we go. Let me find something similar. So first of all, I don't know, like I don't believe I understand your question. So for question 8, nobody asked you to show that it's x squared. That's not the question. In here, you need to decide what is the least integer n, such that f of x is O of x to the power n. And nobody said it's x squared. Actually, briefly looking at some of those, it's actually not going to be x squared. It's going to be something different. So you have a hard time to simplify to x squared because it's not x squared. So when you have a question and you need to decide what is the n, so let's look at something like, I don't know. Which one should we go? Well, let's do the 7a. We have 2x cubed plus x squared log x. In this case, I need to decide which term is bigger, this one or that one. And in this case, I can easily see that this is less than z. Log of x is less than x as long as x bigger than, let's see, 10. This is base 10, correct? Log 10 x to 0 is going to be 1. Well, if you'll take bigger than 10, then it's for sure going to be working. Okay, so in this case, I will have it as 3x cubed. So it's big O of x cubed. So in this case, my answer should be n is 3. That's the answer I'm looking for. Okay. So for each one in your 8, you first need to decide what term is going to be the winning term, which term is the larger term. And after that, you'll have to figure out what to do. Now, in this case, you also do not have to show C and K. You only need to find the bound. That's what they ask for. However, it's a good practice to try and make it smaller. And generally, those inequalities are traditional inequalities. If you do not remember though how inequalities works, it's time to review the algebra of inequalities. Okay. Other questions? Okay, if there are no questions, let's move on to our cool enumeration systems. Okay, so in the enumeration systems, we have where are my notes? We have decimals, binary, octals, and hexadecimals. As I mentioned, decimals are our standard enumeration system. We all love it. It is base 10. Can somebody guess why our human enumeration system, which is the mostly used, is base 10? Correct. It's due to our 10 fingers because it's easiest for us to count by tens because we have 10 fingers and people could show things easily using the fingers. And this is how our enumeration system of 10 came into the play. Now, I did give you a table of how to construct different numbers as long as you go in a traditional order. I really wanted to kind of specify that when you have oops, 10 in different enumeration system, the 10 is going to be representing different things, correct? So how do we distinguish between enumeration systems? Well, generally, when you write a number, we are going to be writing down what enumeration system we use. So in this case, I specified under the parentheses 2, and 2 means binary. So this is a binary number. Now, assume my exercise is to convert the binary number to a decimal number. Those are the ones where my theorem about expansion is going to be helpful. So remember this theorem where it says that every number n can be represented as ak multiplied b to the power k plus ak minus 1 bk minus 1 and so on. So pretty much it can be coefficient multiplier base. Okay, so how can it help us in this case? Well, actually, here is how you do things. So what you always do is you put 2's to a different power. This is your b pretty much. So your b will be b to the power 0, b to the power 1, b to the power 2, b to the power 3. This is your expansion here. So my first here is 2 to the power 0. This is 2 to the power 1. This is 2 to the power 2. This is 2 to the power 3. 2 to the power 4. 2 to the power 5. And 2 to the power 6 expansion. So now on top of it, I'm going to write, well, actually beneath it, I'm going to write it's 1, 2, 4, 8, 16, 32, and 64. And what the expansion means using the theorem, what I have here is I have 1 multiply 64 plus 0 multiply 32 plus 1 multiply 16 plus 1 multiply 8 plus 0 multiply 4 plus 2 multiply 0 plus 1 multiply 1, which is, so 0 multiply anything is just 0. So what I have is 34 plus 16 plus 8 plus 1, which is 89, both with the base 10. So this is traditional number 89. Now, in a similar way, I can do the conversion of octal. So assume I have 2037, and this number is octal. I'm going to do expansion again, but now my base is 8. So every placing represents 8 to the power. So it's 8 to the power 0, 8 to the power 1, 8 to the power 2, and 8 to the power 3, which is 1, 8, 64, and 512, I believe. So now what we got is we have 2 multiply 512 plus 0 multiply 64 plus 3 multiply 8 and plus 7 multiply 1, which is, if you add it up, going to be that number base 10. Now, again, this is this formula with AKs we are using. This is how different enumeration systems work. So you can take any number like that, and you can represent it using different expansion. I can represent 10,055 using binary number, or using hexadecimal number, or using octal 8 base, as long as I know, as long as I expand it correctly. Okay. So now, as you use expansion, the values of A's, so the numbers you see out here, they have to be in between 0 and 8 exclusive. So 0, 1, 2, 3, 4, 5, 6, 7. Those are the only possibilities. In here, my possibilities are zeros and ones. Now we're going to convert hexadecimal. Remember, in hexadecimal, we also use letters because we couldn't represent all 16 different digits using number. So in here, I have base 16. Again, this is 16 to the power 0, 16 to the power 1, 16 to the power 2, and 16 to the power 3. So we have 1, 16, 256, and 4096. Yes, those numbers getting quite big. The next placing is going to be 16 to the power 4, which is going to be already huge. And now, not only we need to convert our 16 to the power 3 to 4096, we also will have to convert letters into values. So just to remind you, we have 0, 1, 2, 3, 4, 5, up to 9. And then instead of 10, we are getting A. Instead of 11, we are getting B. Instead of 12, C. 13, D. 14, E. And 15, F. Okay? So those are the things to remember. So A is actually 10, and we multiply by that. 1 is still 1, so we leave it as is. F is 15, so you have 15 multiply 16, and then we have 3 multiply 1. Now we need to combine all of those numbers, and the answer is going to be 4595 base 10. No, it's not. Wait. It cannot be true. I'm missing a 0 someplace. So, yep, I am missing my 0. Okay, let's redo the calculation. This is 40960 plus 256 plus 240 plus 3, which is Okay. This is 243 plus 256, 499. Okay, are we getting that? Okay. Let me read the chat. It seems like there are a lot of comments here. So after all letters are exhausted, you open up the next spacing. Similarly, like what happens when you run out of the first 10 digits in base 10. So after you got to the number 9, you cannot create numbers which have 1 digit. You'll have to create number with 2 digits. So it's going to be 10 next, 1, 0. Similarly with base 16, when you get to the F, you cannot have a 1 spacing thing anymore. So you open up 1 and you put 0. So actually 10 is 16. No, the smallest hexadecimal number I can represent with hexadecimal is 0. We're not going to go, we're going to only deal with positive numbers for this, but you can also like have negatives if you want to. Okay, next. So yes, AA is a good possibility. In this case, you have 16 multiplied 10, which is 160, and another 16. So it's going to be 176. Okay, and as far as what type of bases we have, I can show you a couple of things. So we're not the first people. We're mostly dealing with numbers because binaries are interesting from the computer science perspective because computers only understand zeros and ones. Well, actually more of a signal on or off, but pretty much we kind of think about it as binary. Now 16s are pretty cool because I'm going to teach you how to easily convert from binary to base 16. Now the beauty of hexadecimals, they're actually more compact than even decimals, and they're more connected to binaries than decimals. We will see it. So it's easy to represent long binary numbers using hexadecimals. And in real life, if you were ever into art, all of the computer graphics, all of the colors are represented using hexadecimal numbers. Generally, it's 6 hexadecimal numbers. Each pair represents the amount of red, blue, and green you need to take when you represent a pixel. So pretty much hexadecimals are used a lot to represent colors. Now, are those the only enumeration systems? Is this always the base or something? People have been using different enumeration systems for a really long time. So this is how Egyptians represented their system, which was also base 10 system, but they represented it using different symbol. So you can see like a line is going to be 1. Our intersect sign is 10. This little roundy is 100. A flower is 1,000. A finger is 10,000. A frog is 10,000 thousands. And then there is a person, Egyptian person in a specific, form, which is going to be million. Now, this enumeration system is antique. And then we had, yes, this was the next one I was planning to show you. Babylonian is also pretty cool. And Babylonians used symbols like, let's hope it's a big picture. Yes, symbols like Z in order to represent it. So they used sticks. One stick is going to be 1, 2, 3, and then they started, they put them down. So they create them by groups, like this is 9. And after 9, they again represent a new symbol for you. And then they start adding those traditional symbols out here. This one is still base 10, and I believe the person who was talking about base 16 meant Mayan. So Mayan enumeration system, which was another antique one, this one is going to be base 20. So they used they combine numbers in a really interesting way. They not only put different numbers, so dots and like football balls and lines. It's also dependent where exactly this stands. So pretty much it not only deals with number of things you see, but also where exactly they are located. So depending on their location, if they're at the bottom, you multiply by 1. If it is in the second, like mid positions, it's by 20. Next ones is multiplied by 20 squared, and so on. So it really depends where exactly it is located, which is pretty cool. But unfortunately, we do not have time to study them. Yes, Mayans were very unique and their system was very great. Yes. So anyway, do we understand how to convert from a numeration system like binary, octal, or hexadecimal into traditional base 10? Do you understand how to do that? Okay. So the next thing we need to learn is we need to learn how to convert. And I'm going to represent it to you using an algorithm, like a pseudocode, which is going to tell you what steps to take, but a bit in computer science language. So base B expansion and B positive integers and P bigger than 1. This is what we got. So Q is going to be N, K is going to be 0. This is how we start, and Q and K are going to be our variables, which are going to compute things. While Q is not 0, we are going to say AK is going to be Q mod B. So B is the base I want to find the expansion to. So you got me decimal number N, and I want to get it expressed in a different numeration system, in binary, for example, or in hexadecimal. This is what this algorithm does. So it says, here is my number N, I want to expand it in B, and B is just number. It's either 2, 8, 16. It can be pretty much any number you want. So what you do first is you create an extra number called Q, and you put all the information from N into it, and you mod it using B. So you do Q mod B. This is a remainder of what happens when you divide the number you received by B. You store it into AK, and then you change Q. You take Q divided by B. This is like integer division. This is the whole portion. This is the quotient, correct? So AK is your remainder and Q is your quotient. And then you're going to say we need to change our K to go up. And we are going to loop here. You can see that Q is going to be changing every time. And we are going to be generating a new AK every single time. Then at the end, we want to return a number AK plus 1, AK minus 1, A1, A0. So you want to return all the digits you have calculated. So you calculated many AKs. You want to put them in the order with the very first one to be on the right. And this is going to be your expression. Let's try it. So assume I'm going to give to my algorithm 97651, and I am going to try and get it to base 16. So I have a traditional number 97651, and I want to get it to base 16. The first thing I'm going to do is I'm going to say, okay, 97651 is equal to 16 multiply 6103 plus 3. So remember, what I do is I mod B, correct? So I'm trying to divide it by 16. And I need to find my quotient and my remainder. And this is what we did. We found quotient and we found remainder. Now my new Q is going to be the quotient. And I need to repeat the process. Okay? First of all, see that I stop that my quotient is equal to 0. 6103 is not 0, correct? So I need to do it again. So now we're going to represent it again is 16 multiply 381 plus 7. Now we do the same. Q is the new quotient, which is 381. It is still not 0, so we still need to do it. So it's 16 multiply 23 plus 13. So plus 13. The next one is going to be 23 equal to 16 multiply 1 plus 7. And then we have 1 equal to 16 multiply 0 plus 1. And now we need to create our number. Now, one thing to remember, those numbers here are my A's, correct? And the very first one is A0. So this is where it's important. People do get confused on it. You put A0 at the right. So we're kind of going 3, 7. Now, what can you tell me about 13? Can I put 13? Is 13 hexadecimal? No. What do I put instead of 13? What is 13? Yes, 13 is D, 7, and 1. So this is the hexadecimal representation of 97, 651. And you can try and get it back later. Now you can do it for any enumeration system. You can put 2 instead and so on. So the way you do it is you always try to find the remainder and quotient, and then you replace your number with the quotient and repeat, repeat, repeat. What it really does, it pretty much tells you how many times thing fits in, what is going to be multiple of 16, and you will be able to represent it using higher digits because it's already 16 multiplies something, correct? So it's 16 multiplies 6,103. So that means I need to start at a second portion in order to represent it. And then the remainder is what doesn't fit into 16 anymore. So this is really the idea of quotient and remainder, correct? You're trying to divide it equally, but sometimes you have a remainder. You do not want somebody to get offended and not get it. So what stays with you, what you cannot give anymore because you have too many people, okay? So now it's time for us to learn how to convert binary to other. And listen carefully because this is the best trick and you want to use it during the discussion section today. So assume I have a really long number. Yes, something like that. It is a binary number, so it's base 2. And I want to convert it to hexadecimal. Oh my God, converting this one to traditional decimal is going to be a lot of work, correct? There is a lot of placing and you need to do 2 to the large pi. Is there a better way to convert it to hexadecimals? Yes, this is a group of 4. That's correct. The trick is you always start from the right and you generate groups of 4. So you take 4 digits together like that. And then you think about every group of 4 as just a number, okay? So what is the number 1101? Well, 1101 is 13. And then this is 4. 0100 is 4. And then this is 12. And this is why I hope you wrote the ugly table I was trying to create for you last time, because it had all the first 16 binary numbers, correct? So now it's supposed to be a lookup table for you. So then we have 3 and 1. So this number in hexadecimal is 1312. Oops, 13. Can I put 12? No, what do we put? See, it is 4 and D. Good, so we have converted it. Now, what about octal? Well, actually, octal also has a trick. Now we're going to do groups of 3. Like that. So what we have here is 5, 1, 1, 6, 3, and 2. And my number is going to be 2, 3, 6, 1, 1, 5 in octal. Now, if you do need to convert it to the decimal, you might prefer to do it either from hexadecimal or from octals, just because it's not going to be as many 2's to the power, because in here it's like really easy to mess up and forget about one of the 2's, like jump from 2 to the power 3 to 2 to the power 5 instead of 2 to the power 4. So be careful when you do those things. Now, why does this trick work? Well, if you think about it, what I get here is let me write it for you down. It's 2 to the power 0, 2 to the power 1, 2 to the power 2. This place in here is 2 to the power 3, which is 8, correct? So now, if you think about it, those 3 digits I have here, yes, those digits I have here, they're kind of 2 to the power 3, and then 2 to the power 2, 2 to the power 1, and 2 to the power 0. Do you agree? If I kind of factor it out. So this is pretty much 8 multiply this number, agreed? So, but what is this place here? It's 8 multiply that number, correct? Because it's 8 to the power 1. And if you go, keep on going, this is 2 to the power 6, correct? So you will be able to factor 2 to the power 6. Yes, which is going to be 64. So this is how it works. And same for hexadecimals. It's kind of cool, but it works. Okay, great. Next. So the next thing I want to talk to you about is how logic operations are still different from traditional addition. So what is the difference between bit operations like OR and 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 traditional addition and multiplication? They're really different, correct? So pretty much they have a different logic. With the bit operation, you just look at every single bit. You do not remember anything from previous. However, if I have 2 binary numbers and I want to add them together, if it is an addition, we're going to be using the same tricks as we did with the addition of decimal numbers. You do not look anymore just at every digit separately. You look at it as a whole number. So if you have 1 plus 1, it's supposed to give you 2, correct? And 2 in binary is remembering 1 and putting 0 here, correct? Because 2 is 10, right? Agreed? So now I need to add together 1 and 0. So I'm going to put 1 here. Then we do 1 plus 0, which is 1. And then we do 0 plus 1, which is still 1. And now things get again complicated because 1 plus 1 is 2. So I need to put in 0 and remember 1. And now this is where things get even more complicated because I have 3, correct? And 3 is actually 11. It's 1, 1, correct? 3 is 1, 1. So I need to write 1 and put 1 out here. So then we got 1 here. And again, one more time, I put the 10 here. So here we go. This number is going to be my addition. Very different from XOR, like not connected, very different from AND or. All of those are cool operations, but this is traditional addition, just in binary, okay? So what about multiplication? Well, guess what? Multiplication is going to work again like our traditional multiplication. So we are going to first multiply 0 by every single number here. So it's going to be 0, 0, 0, 0. Then we need to go one space down, correct? And we need to multiply y by the number. So it's 1, 0, 1, 1. Then we need to multiply third one and put the number again. Now the beauty is that because we have either 0 or 1, we only have 2 options. Either we put all zeros or the number itself, correct? Because 1 multiplied number is the number itself. And now we need to do the addition. So it's 0, 1, 1, 1, 0, 1, 0, 1. So this is the number we are going to get. Okay. So this is how binary addition works. Our textbook actually represents it also as algorithm and the pseudocode. So if somebody wants to try it, you can really write a program to actually do it for you. Okay, so last thing I want to talk to you about from this session is GCD calculation. So when you have two numbers and you want to compute GCD of A and B, the way you do it is you first and let me, in case somebody doesn't know, we are looking at greatest common divisor. So the way you do it is, again, you represent it as A equal to B multiply Q plus R. And then you repeat it with B equal to R multiply Q plus new remainder. And then you move on like this over and over again. So let me try and be consistent with the textbook. I want to use the same letters in case somebody reads it. I do not see it. Anyway, fine. My Q is going to be A. My R is going to be, well, I don't need it. Okay, so while B is not equal 0, Q will be getting A division B, and R is going to be getting now one thing. In computer science, you need temporary value to store it, but in pseudocode, I can just say old QR are used, correct? Not the new ones I'm just replacing, but the old ones, correct? So those are the Q and R's. I'm using it, I'm changing them. And then at the end, my GCD is going to be B. My GCD is going to be the last remainder I got. Okay. Where is my notebook? So let's try and do it. The operation of div, it's a quotient. Again, in programming on Python, and it's traditional integer division in Java. Okay, so your homework assignment from section 4.2 is 2, 4BD, 6BD, 8, 12, 23C, 24AC, 26, and 28. And we are going to go into 4.3 and talk about primes and GCD. Keep on talking about it. So first, let me define something which you all already know. An integer p strictly bigger than 1 is called prime if the only positive factors of P are 1 and P itself. If something is not prime, that means it's composite, composed, or multiplication of two integer. Okay? So 11 is prime. 41 is prime. Now, there are infinitely many primes. $39 is 3 multiply 13, correct? So composite, not prime. Ten is composite because it's 2 multiply. Cody, I love the joke. Yes, 2 is composite as long as it's in decimals because it's 2 multiply 5. But in base 2, 1, 0 is 2, so 2 is prime. Now, also notice that the way I defined it, 1 is also not prime. Okay? Now, there is a lot of conversation going on generally about is 1 prime or not prime. It really depends how you define it. You can say 1 is an exception and it's a prime. You can say it's not. P1 is pretty much very special, correct? 1 can generate everything, right? 1 is a starting number. So, theorem. And I'm running out of time, but we will write it and we will talk about it next time. It's called fundamental theorem of arithmetics. And it says every integer greater than 1 can be written uniquely in the form n equal to p1 to the power a1, p2 to the power a2 multiply pk to the power ak, where pi's are primes and ai's also belong to positive, generally integers. And again, n is an integer, so we can always represent it like this. So powers of primes. Every number can be uniquely represented. I do not care about order. On that note, we are done, and I'll see you on Friday. Enjoy the discussion today. Oh, yes, and on Friday, you will just see me talking because it's going to be recorded. Yes? No real meeting. You can just watch what I post. Have a good day.